Imagine a massive ship, a floating city of steel, trying to hold its position perfectly still in the middle of a churning sea. It's not magic, it's technology. This is the job of a dynamic positioning, or DP system. These incredibly clever systems use a network of thrusters and propellers to counteract the forces of nature. They are the brains of the operation, constantly calculating and adjusting to keep the vessel exactly where it needs to be. Whether it's a drill ship working deep in the ocean or a supply boat next to an oil rig, staying put is absolutely critical. A few meters of drift could be disastrous. It's a constant battle against the elements. To win this battle, the DP system needs to know its enemy. The enemy in this case is the environment itself. The wind, the waves, and the ocean currents are all trying to push the vessel off course. You can't just guess what these forces are doing. You need to predict them, to understand them with incredible precision. This is where mathematical models come in. These are not physical models like a toy boat in a bathtub. They are complex sets of equations running inside the DP system's computers. They act as a virtual simulator, constantly telling the ship what the environment is throwing at it. These models are the secret sauce of dynamic positioning. They break down the chaotic forces of nature into numbers the computer can understand. Think of it like a weather forecast, but for a single ship, and it's updated every single second. The system needs to know how a gust of wind will affect the tall cranes on deck, and how a slow-moving current will nudge the enormous hull below the waterline. Without these models, the DP system would be flying blind, reacting too late and using far too much fuel. Getting the models right is the key to safety, efficiency, and success. So how does it do it? The system splits the problem into two parts. It looks at the world above the waves and the world below them separately. One part deals with everything happening in the air. That's the aerodynamic model. The other handles everything happening in the water, the hydrodynamic model. Each model focuses on a different set of forces and behaves in a completely different way. By understanding both, the DP system can build a complete picture of the environmental forces, allowing it to command its thrusters with pinpoint accuracy and keep that massive ship steady as a rock. Let's start with what happens above the water. This is the domain of the aerodynamic model. The name sounds complicated, but the idea is simple. It calculates the force of the wind pushing against the ship. Everything that sticks up out of the sea, the hull, the accommodation block, the cranes, even the lifeboats, acts like a giant sail. When the wind blows, it pushes on this exposed area, trying to shove the vessel sideways or twist it around. The aerodynamic model's job is to figure out exactly how strong that push is and from which direction it's coming. It's a constant, invisible force that can change in a heartbeat. The main input for this model is, you guessed it, wind. The DP system gets its information from anemometers, which are special wind sensors mounted high up on the vessel. These devices measure wind speed and direction in real time, but the model is cleverer than just taking a single reading. It knows that the ship's own shape will affect the wind flow around it. So, the model contains a detailed map of the vessel's superstructure. It uses a formula that combines the wind speed, the air density, the shape of the vessel, and a special number called a drag coefficient to calculate the final force. The maths behind the aerodynamic model is relatively straightforward. It often uses a formula that looks something like this. Force equals half the air density, times the wind speed squared, times the exposed area. The squared part is important. It means that if the wind speed doubles, the force it exerts doesn't just double, it quadruples. This is why sudden, strong gusts of wind are such a big deal for a DP operator. The forces can ramp up incredibly quickly, and the DP system needs to react just as fast to keep the vessel under control. One of the defining features of wind is its volatility. It can change speed and direction in an instant. A sudden squall can appear out of nowhere, hitting the vessel with a powerful punch. The aerodynamic model is designed to handle this. It processes data very quickly, providing the DP control system with immediate updates. This allows the thrusters to fire up and counteract the wind's effect almost as soon as it happens. For a DP system, predicting the wind is all about rapid response and staying one step ahead of the next big gust. Now, let's dive beneath the surface. This is where the hydrodynamic model takes over. This model deals with the forces acting on the part of the ship that's underwater, the hull. Water is much denser than air, about 800 times denser in fact. So, even slow-moving water can exert enormous forces. The hydrodynamic model has to account for two main things: the ocean currents, which are like slow, powerful rivers flowing in the sea, and the waves, which create their own complex motions. These forces act on the huge submerged area of the hull, pushing and pulling it with immense, steady power. The inputs for the hydrodynamic model are more complex than those for wind. Current speed and direction are key, but they are often harder to measure directly. Some vessels use acoustic sensors called ADCPs, acoustic Doppler current profilers, to get a picture of the water column. But the model also has to consider wave action. It uses data from motion reference units to understand how the vessel is rolling, pitching, and heaving. The model then uses this information, along with a detailed three-dimensional map of the hull's shape, to calculate the forces at play. It's a much slower, heavier dance than the one happening in the air. The mathematics of hydrodynamics are significantly more complicated than aerodynamics. Water doesn't just push, it flows around the hull, creating areas of high and low pressure, suction and drag. The model must also account for something called added mass. When you try to move the hull through the water, you also have to move a large amount of water with it. This makes the ship feel much heavier and slower to respond than it actually is. These calculations are incredibly intensive, involving complex fluid dynamics equations to accurately predict the vessel's slow, lumbering response to underwater forces. Unlike the fast-acting wind, hydrodynamic forces are generally slow and predictable. A strong ocean current doesn't just appear out of nowhere. It builds gradually and remains steady for long periods. This gives the DP system more time to respond. However, the sheer power of these forces is immense. They are like a giant hand, gently but unstoppably pushing the vessel. If the hydrodynamic model is wrong, the DP system might constantly fight a force that isn't there. Or worse, fail to counteract a real one, leading to a slow but dangerous drift off station. So we have two different models, one for the fast, flighty wind and one for the slow, powerful water. Neither one is enough on its own. The real genius of a dynamic positioning system is how it blends them together. The DP control system acts as the conductor of an orchestra, taking information from both the aerodynamic and hydrodynamic models to create a single, unified command for the thrusters. It constantly weighs the influence of each force, deciding which one is the bigger threat at any given moment. It's a beautifully coordinated balancing act. In practice, the system is always listening to both. On a calm day with a strong current, the hydrodynamic model will be the star of the show. The DP system will apply a steady, constant thrust to counteract that slow, heavy push. But if a sudden storm blows in, the aerodynamic model takes center stage. The system will need to make rapid, powerful adjustments to fight the violent gusts of wind. The operator can see all of this on their screen, watching as the system allocates power to fight the invisible forces reported by the models. The importance of getting these models right cannot be overstated. A poorly calibrated aerodynamic model might cause the vessel to overreact to small gusts, wasting fuel and putting unnecessary strain on the machinery. A flawed hydrodynamic model could lead to a slow-off, where the vessel drifts away from its target position so gradually that it becomes dangerous before anyone notices. For a DP operator, understanding how these models work is fundamental to their job. It allows them to interpret the system's behavior and make critical decisions, especially when conditions get rough. Ultimately, these models are the bedrock of maritime safety and efficiency in a huge range of offshore operations. They are the invisible intelligence that allows colossal structures to perform delicate tasks in the world's most challenging environments. By accurately predicting the forces of wind and water, the aerodynamic and hydrodynamic models work in perfect harmony. They give the DP system the foresight it needs to hold its ground, ensuring that every operation is not just possible, but safe. It's a remarkable fusion of physics, mathematics, and engineering that keeps our modern maritime world running smoothly.